And if you're on spring break and you're here, that's great. So to make the most of our time together, realize that even though it's spring break, we want y'all to keep track of the things you know well and keep track of the things you need to ask questions about. And realize that the AP exam is coming in May, and it doesn't really ask you if you're ready or not. So the goal of these is to give you a little bit of stuff that you covered a long time ago, make note of the thing that you do really well on, and make note of the thing that you need to work on. And then as you get into May, you can really study those things that you needed to work on the most. And the stuff you were good at, you shouldn't need to worry about. So it's studying smarter, not necessarily harder, although some of you probably need to study both harder and smarter. So we're going to go ahead and get started. So we've done Unit 1, and just to catch you up, Unit 1 was about the atom. How many protons and electrons does something have? And then how do we know how many electrons that has? Where are they? Electron configurations. What properties do the number of protons and electrons and where they are? What properties does it give that element? And we call those periodic trends. In Unit 2, we then moved from individual atoms into molecules. So for molecules, it's all about, okay, now that we've got things bonded together, what are the different types of bonds? So Unit 2, we talked about metallic bonds, ionic bonds, covalent bonds, Lewis structures. So what's the best Lewis structure? And then we talked about, well, what is the shape once you know the Lewis structure? Or what is the angle between elements when you know the Lewis structure? And is that molecule polar or non-polar kind of a thing? Right? So in Unit 3, we're talking about intermolecular forces. So you can see how this goes. Unit 1, atoms. Unit 2, molecules. Unit 3, now this is between two molecules. So we're not talking about just water molecules. We're talking about what are the IMFs between two water molecules. And what does this do for us? So that's kind of everything that we're trying to do today. Included in this is a little bit of what makes an acid an acid, acid and acid. What makes a solid, a liquid, and a gas, and how are those properties connected to those intermolecular forces? So let's go ahead and get rolling. The very first question. Tonight, I'm not wearing a hat. Many of y'all have pointed out that I'm not wearing a hat. So these are your choices. You can either choose hot dog hat, elephant hat, or chicken hat. Or if you just don't want to see a hat at all, that's a choice as well. So go ahead and go to joinpd.com if you haven't already and enter the code KFXKWG. And I have all three hats ready. So whatever y'all pick, this is going to be epic. And I got to tell you, it's really hard to find a picture of intermolecular forces with hats in it. So good for me, right? So, all right. Elizabeth Busby, James Clemens, if they choose D, that's fine. A choice is a choice. That's fine. All right, let's see what the answer is. So B by a long shot. So let's see, what was B? B was elephant. So let's see. Elephant. All right, now on with the show, on to actual chemistry. So this is just a question just to kind of see where we're all at. So again, using Pear Deck, what do you think solid ethyl alcohol would be? So this is ethanol, but not in a liquid form, in a solid form. Which one of those choices best describes solid ethyl alcohol? Keep in mind that in Pear Deck, I don't know what your answer is. And keep in mind at the end of this, you should get a takeaway sent to your Google Drive, although some people's filters have been blocking that, so maybe you won't. But we try to send them. But answer honestly, and I'm never going to chastise y'all for being wrong, because again, the point of these review sessions is not to say, haha, you're wrong. The point of these review sessions is to say, hey, this is something I need to work on, right? So it's all about getting better before the big AP exam. So let's see what y'all are showing for an answer. Mainly C, no E's, mainly C's, okay? So let's see if you guys are right. A molecular solid with hydrogen bonding. Well, it's kind of hard to know if it's hydrogen bonding or not because it's like you haven't drawn out the Lewis structure. But my guess is, yes, it has some hydrogen bonding. A molecular solid with zero dipole moment is a fancy way of saying it's not polar at all. And I will tell you, anytime you have a molecule made up of different elements, like carbon, hydrogen, and oxygen, it's going to be at least a little polar. So typically, saying zero dipole moment is kind of a tough barrier to hit, all right? And it's definitely not ionic. We did this last week. Ionic stuff is made up of metals and nonmetals. And if you said metallic solid, then you don't deserve it because, hey, there's no matter present. But that's the different types of bonds that we see. Is we see covalent, we see ionic, and we see metallic. All right, so just you guys have covered this, so I'm not here to teach y'all all this, but kind of just go over all the types of IMFs, right? So when something is polar, we say it has a dipole. So we're right there in the middle where it says dipole, dipole. Anything that's polar, it has a positive end and a negative end. And what causes those positive and negative ends is the electrons are not distributed evenly over the whole molecule. One end of the molecule has got the electrons more. Why? Because it's pulling on it harder more. What do we call that? Electronegativity, boom, dropped it, unit 1, 2, and 3. So a dipole is induced when you get an uneven distribution of electrons. When one thing that's polar is attracted to another thing that's polar, we call that a dipole-dipole force. Now, there are several different types of dipole-dipole. We have some very, very weak dipole-dipole forces that we call London dispersion forces. Those are things that are polar only for a brief second. For a brief moment, they're polar and then it's gone. So these are not constant polar attractions. These are instantaneous polar attractions, meaning it's there for an instant and then it's gone. And we call those London dispersion forces. Then we've got dipole-dipole forces, which is something that's polar is attracted to something that's polar. And we call those like it's a constant dipole. So in other words, it's not just dipole for a brief moment, it's always polar. And then you've got super duper dipole-dipoles. These are not things that are just polar. These are things that are crazy polar. How do you become crazy polar? Well, you have something that's hydrogen, which ain't electronegative hardly at all, attracted to something like N, O, or F, the three most electronegative elements on the periodic table. So we say to have a hydrogen bond, which is just an uber dipole-dipole force, super strong dipole-dipole force. To have an H bond, you have to have a hydrogen that's stuck to N, O, or F. And then that hydrogen has to be attracted to an N, O, or F on another molecule. So it's kind of a high bar to give it that super polar dipole-dipole force. We call that a hydrogen bond. You can also have an ion dipole when something polar is attracted to an ion. Think about salt water, right? You got salt, sodium ions attracted to water molecules. And then we've got the induced ones. So an ion can make something that's normally not polar at all polar. So an ion-induced polar. And then you've got a dipole-induced dipole. So something that's polar causes something that's non-polar to be polar for a brief moment, just by getting close to it, right? Now, notice these numbers in the table are all over the place. 40 to 600, 10 to 40. So a lot of your teachers are like, what's the strongest intermolecular force? And some of y'all have been taught hydrogen bond. Hydrogen bond is not always the strongest. intermolecular force. How do we know what the strongest intermolecular force is? Comes down to the data. So you're really going to have to look at the data for melting point and higher and boiling point. And the higher the melting point is or boiling point, the greater the intermolecular forces are. So something like concrete has so many ionic forces holding it together, it really doesn't melt. Salt won't melt until it's 700 degrees. So salt is basically a rock that has such strong attractions between the ions that it's so tough to pull apart. It has a super high melting point. So we always base it on the data. Don't just always go, hydrogen bond, got it, always stronger, because it ain't. Because notice that a hydrogen bond can be 10 to 40, and notice that a dispersion force down at the bottom can go all the way to 40. So you have to kind of keep that in mind of what's going on. All right, we've brought it up in Unit 1 and in Unit 2 and in Unit 3. What governs how strong a force of attraction there's going to be? Coulomb's law, again. Well, that was last week. So this is Coulomb's law againer, because we do it again in Unit 3. Basically, here's the thing. When you don't know what the answer is, it's either hydrogen bonds or Coulomb's law. Just tell your teacher Coulomb's law when you don't know. They'll be very excited I told you to do that. But Coulomb's law is, again, Q1, Q2 is how big the charge is, and R squared is the radius. So you want a bigger charge and a smaller radius to give a really strong force of attraction. Now, when we say molecules are polar, they don't have a charge of like +1, +2, or -3. When things are polar, they have what we call a partial positive or negative charge. But partial positive and negative charge, you can still have a small partial positive charge or a large partial positive charge. And the bigger the partial positive charge, because they're more polar, the greater the force of attraction. So Coulomb's law still reigns when we come to IMFs. So solids, liquids, and gases. Notice the solids are very tightly packed together. They cannot move past each other. Doesn't mean they're not moving. Solids are vibrating. So solids do have movement. They do have kinetic energy, and their kinetic energy is tied to their temperature. So the warmer it is, the more kinetic energy it has. And the more kinetic energy it has in general, the faster it's going. Liquid, notice, are still stuck to each other, but liquid molecules have the ability to slide past each other. And why is that? That's because they have enough energy to break some of those intermolecular forces. So a solid is tightly bound because those things don't have enough energy to break those intermolecular forces. The liquid does have enough energy to break some of them and slide past each other, while a gas has enough energy to break all of the intermolecular forces and escape so that there are individual molecules in the air. Now, something I want you to notice about the picture, the length of the arrow in the picture indicates speed. So a little bit later, I'm going to ask you to draw a picture, and I just want you to think about the length of the arrow indicates speed. And of course, all the molecules would be moving in different directions. So it's not like all the molecules slide to the left or all the molecules slide to the right. They're really just bouncing all over the place. We call that Brownian motion. All right. So in terms of solids, you've got a couple different types of solids. So you can have solid atoms. So like think carbon, solid carbon, right? Or solid neon, if you got neon cold enough. You've got molecular solids, and that's like ice, right? So you've got a molecular compound like water, and it's stuck to other water molecules with some kind of IMF. You've got ionic solids, and ionic solids is salt, right? Sodium chloride and a sodium and chloride are all stuck together into what we know as salt. You've got metallic solids, and those again are just metals that kind of hang out. And the one I want you to know in particular is called covalent solids. The other word for those covalent solids is covalent network solids. These are special things. Covalent network solids are things where they're not molecular stuff, covalent stuff with IMFs between it. No, covalent solids are all covalent bonds all the time. All covalent bonds all the time. So these are things with only covalent bonds. These are things like diamond or quartz or silicon dioxide. Think of sand or granite, right? All those things have those super strong covalent bonds everywhere. And because of that, those things will have those network solids, covalent network solids, will tend to have the highest melting point of anything, just because it doesn't have IMFs so much as it has covalent bonds everywhere. All right, so let's give this one a try. Now, hang on for just a second, because I don't want you to answer part D. So just follow along. You guys actually looked at part D last time. So I'm trying to show you how they build a question. So they're going to have you draw a Lewis structure, right? That's fine. We did this last week. That's fine. Part E, what is the approximate value of the bond angle? We did that last week too. So where does unit 3 come in? Unit 3 comes in this, the C2H4 and the C2H5OH pass through a tube into water. The C2H4 was collected as a gas, but the unreacted C2H5 was not. Now, in the question, they actually gave you a diagram of the setup of this, but basically the gas was bubbled through water. The gas, the C2H4, came up out of the water, but the C2H5 did not. So it asks you to, why do you think that's true? So if the C2H5OH didn't bubble out, that means it must have mixed into the water. So that C2H5OH gas stuck to the water molecules. So knowing that the C2H4 came out of the water and the C2H5OH stuck to the water, take a stab at using Pear Deck and explain this observation in terms of the intermolecular forces between water and each of the two gases. I'm seeing several of y'all saying you didn't get a Pear Deck link from last week. What I think probably what you ought to do is you should reach out to your teacher or talk to your teacher and have them reach out to Mr. Matt Dean, and maybe he can look at getting you that Pear Deck link. But the other thing to know is every single one of these is being recorded and they're being put out on YouTube. So if you need to, you can also go back and review this material that way. And Matt put in the chat box to email Matt, and he will try to get you your Pear Deck file. Seems to be a big problem, both Joey and Neha. Some people's spam filters are blocking them from going through. So, all right, so let's see what we've got. I got 43 answers, so I'm just going to look at a couple of them real quick. C2H4 has covalent bonds, whereas C2H5OH has hydrogen bonds.
It's so much fun.
The C2H4 did not stop in the water because it is nonpolar. The C2H5 is polar. The water has a stronger bond because its hydrogen bonds have a stronger attraction. Stuck to the water molecules due to being polar and having a dipole to dipole movement. I think maybe you meant to say moment. Okay, so I'm seeing lots of good answers. Here's one about boiling point, but keep in mind you don't have any data that backs up that boiling point. So avoid whoever said the C2H5OH has a higher boiling point, ones were stronger. You don't have any data to support that. So the question says they both came through as a gas. So be careful to base it only on what the question says. So let's talk about what the answer here should have been. And I'll try to point out some of the way y'all could have made your answers better. So C2H4 is a non-polar molecule. So anything with just carbons and hydrogens is not polar enough to be what we call polar, right? So just hydrocarbons are non-polar molecules. So that means it's only going to have like London dispersion forces. The water is capable of having dipole-dipole forces. It is polar. And it's also capable of having hydrogen bonds. So the best answers would look like this. Water and the C2H4 would only have dipole-induced or just London dispersion forces. And then the C2H5OH, the alcohol, it has the ability to hydrogen bond with water, and it has those London dispersion forces, because remember, anything with electrons has London dispersion forces. So you can't say, oh, it's got hydrogen bonds. Remember, they both have London dispersion forces, but the alcohol in this case stuck to the water because it has those hydrogen bonds. So you need to make sure you note not only that it's polar, which is true, right, the C2H5OH, but you need to say, it's polar and that lets it hydrogen bond to the water, whereas the C2H4 only had London dispersion forces. And that's where the question says, explain this in terms of the intermolecular forces between water and each of the two gases. So if you only talked about just the C2H5OH, you wouldn't get the point, right? So just make sure you're reading the question and you're answering the question. If it says each, then make sure you talk about each one. Matt also said, if you're having trouble getting your takeaways file at the end for Pear Deck, next time you could try using a personal email account, like a Gmail account or personal one to log into Pear Deck and see if that helps. See if then it's not getting sent through the school folder. So that's if you feel comfortable with that. All right, so here's a multiple choice question that you would see about the higher boiling point and stuff like that. All right, so notice the molecules. Nonane is, again, a hydrocarbon, and trifluoropentane is a hydrocarbon, but it's also got fluorine on it, right? So if they have identical molar masses, here's what they're trying to tell you. They're trying to tell you if they have identical molar masses, then it's going to have about the same number of electrons, and it's going to have pretty much the same London dispersion forces, right? So anytime they're telling you, hey, look, the molar mass is pretty much the same, they're trying to say, hey, look, the London dispersion forces will be about the same. So which one of those four answer choices is best to explain the difference in boiling point, right? So go ahead and use your Pear Deck thing and come up with what you think the best answer is. All right, I got 31 so far. That's great. And again, if you missed this question, I don't know that it's you. I don't know that it's Isabella or Isaiah or Wicker or Brooke. So I don't know that it's you. So go ahead and answer. And the goal here is to find out what you're good at and the things you need to work on some more. All right.
Hey, Danny,
so
can you read out answer D? Some people can't see it. The Pear Deck's cutting it off at the bottom.
Oh, my bad. Yeah, let's see. I don't know if I can or not. Let me see. Let me go over here. The carbon chains are farther apart in a sample of nonane than they are in 2, 3, 4 trifluoropentane. That's choice D. The carbon chains are farther apart in a sample of nonane than they are in the sample of 2, 3, 4 trifluoropentane. So the first molecules are closer together than the second molecules. I'll work on that for next week. All right, let's see what y'all thought the answer was. Ooh, lots of C's. A decent number of A's. And some B's. Okay, so a lot of y'all are changing your answers and you're going to be sad. So the correct answer there is the fact that the nonane is longer means it has more like surface area with which it can form those intermolecular forces. So even though trifluoropentane is polar, you're like, oh, the CF bond is more polar than the CH bond. That's a good thought, right? That was a good thought. But if it's more polar, then it should have a higher boiling point. And when you look at the data, it has a lower boiling point. So the one with the higher boiling point, the nonane, must have the stronger intermolecular forces. So if it's not the polarity thing, and it's not the number of London dispersion forces, it's that C, the carbon chains are longer in nonane than they are in the other one. Think about if you have the molecules stretched out like that, there's more individual places where you can form those intermolecular forces. Now, the reason why A is wrong is you have to keep in mind when you boil a liquid, you're not tearing that liquid apart into elements. So you're not breaking that CF bond when you're boiling something, and you're not breaking the CH bond. Those are the covalent bonds inside the molecule. What you're breaking is you're breaking those intermolecular forces between two nonane molecules or between two of the trifluoropentane molecules. All right, so you guys had some good answers in there. Here's another one. You can just type out your answers here. What are the types of intermolecular forces in glucose, which is on the left, and cyclohexane on the right? Go ahead and type out, what do you think all the types of IMFs or intermolecular forces are in pure glucose and pure cyclohexane? And by the way, if you don't know it by now, intermolecular forces is the stuff. That's the thing that y'all tend to get wrong the most on the AP exam. And when I ask your teachers, by and large, what are you guys really good at and that you don't need help with? They say intermolecular forces. So what that means is you guys really need to, in May, go back over those intermolecular forces. Find some questions that help you review that material because they are all over the AP exam, asking you to look at data and there's always something on the free response questions about it. So I'm just going to look at a couple of the answers. This time I'm going to scroll down to the very bottom and say, okay, London dispersion, dipole-dipole, and hydrogen bonding. London dispersion, hydrogen dipole-dipole, hydrogen and ionic. LDFs, yeah, you don't have to type London dispersion. This is a good point. You could type LDF. They totally know what that is. And you could also say H bonding, right? Covalent dipole-dipole and London dispersion. They both have LDFs. Okay, great answers. So first of all, I am so proud that you guys said that they both have LDFs because that's the one that y'all typically missed. You're like, aha, it has oxygens and hydrogens. It's going to have a hydrogen bond. But you always have to remember, everybody has London dispersion forces if they have electrons. So pure cyclohexane, remember I told you, pure cyclohexane is a hydrocarbon, and hydrocarbon only have those LDFs, those London dispersion forces. Whereas the molecule on the left, the glucose, will have dipole-dipole forces. It will have London dispersion forces, and it will also have hydrogen bonds. So let's see where the question went to from there. Glucose is soluble in water, but cyclohexane is not soluble in water. Explain. So go ahead and take a stab. I'm going to eat a tortilla chip because I haven't eaten dinner yet. Why would glucose, the molecule on the left, be soluble in water, but cyclohexane is not soluble in water? As y'all are answering, Pranay had a question. Can you say LDS and IMFs on the AP exam? Yes, you can. But don't say like DPs or anything like that. Just try to stick with only abbreviating some things. LDFs, IMFs, don't abbreviate everything. Because remember, they have to try and figure out what you're saying. And if you abbreviate everything, then the readers will have no clue what you're talking about. All right, let's see what y'all's answers are. This time I'm going to scroll to the middle. All right, the H bonds in glucose, which the cyclo doesn't have, interact with the water molecules. Okay, there are no oxygen atoms to attract the hydrogen atoms in H2O, causing the C6H. No more tortilla chips for me, causing it to not dissolve. So I want y'all to listen to this answer and see how we can make it better. There are no oxygen atoms to attract the H atoms in water, causing the C6H12 to not dissolve. Even if I thought the student was maybe on the right track, couldn't give them the point because who doesn't have any oxygen atoms? So try to phrase your answers in complete thoughts. If you're trying to say the C6H12 has no oxygen atoms to attract the hydrogen atoms, that's a better way to answer that. Because it has hydrogen bonding and it is attracted to the water molecules. Again, try to avoid its. And because if you want to say glucose, because you want to earn the point, then say glucose. Glucose has hydrogen bonding and the OH ions will bond with water molecules. Okay, so keep in mind, there are no OH ions. So this is a good lesson in what will lose you a point. That molecule is covalently bonded. You may be doing acids and bases right now, and you just have OH ions on the brain. But just keep in mind that that Lewis diagram that they drew for you, that had the OH attached. So if you want to say the OH group, that's okay. Glucose is soluble because it contains hydrogen bonding and LFDs. Can't give you a point for LFD. And so does water. So there's attraction between glucose molecules and water molecules. So I think y'all are getting very, very close on a lot of the answers, right? So what would the best answer look like? Well, glucose can bond using hydrogen bonds to water. So polar things tend to dissolve in other polar things. While cyclohexane only has those London dispersion forces and non-polar things don't really dissolve into polar things. So the bar for this one was pretty low. But as long as you're indicating that glucose has strong IMFs like hydrogen bonds with water, whereas cyclohexane only has very weak IMFs with water, that would probably earn you the point. All right. Let's see where the question went next. Consider the two processes below. So water liquid turning into water gas and water liquid turning into hydrogen and oxygen. So that's the difference between 1 and 2. For each of the two processes, identify the type of intermolecular or intra, that means within, intramolecular attractive forces that must be overcome for the process to occur. So go ahead and take a stab. Keep in mind it says for each. of the two processes. So you want to talk about process 1 and you want to talk about process 2. What type of intermolecular or intramolecular attractive forces must be overcome for the process to occur? Okay, I got 31 answers so far. I'm just going to peek in and see what y'all are putting. So be careful saying process 1 has intramolecular and process 2 has intramolecular, because they want to know what intermolecular and what intramolecular force. It's not enough to use the same word. You're going to have to refer to a specific kind of force that's doing that. Okay, y'all giving lots of great answers. Y'all are on the ball tonight. This is great. So this is a question from like 2008, just so you know. It would be worded a little bit differently in 2021, but the basics are still pretty much the same. Y'all are giving great answers, right? Okay, so just to keep using our time wisely. So in process 1, really what they were looking for is hydrogen bonds, right? That's what they look for. Now, if you said hydrogen bonds and LDFs and dipole, great, that's fine. But you had to have at least those hydrogen bonds that hold liquid water together. And when you turn into a gas, you break those. And then for process 2, basically what they're saying is, can you point out that in process 2, you're breaking the covalent bonds inside the molecule? So they're getting you to differentiate between the intermolecular forces, the hydrogen bonds holding water together, versus what holds an individual water molecule together. And those would be covalent bonds, right? And the question is not quite finished. So let's see what it did. And I'm going to have to read part of this to you. So, because I cut it off. So that's my fault. So let me read you this very last statement. So the very last statement is, indicate whether you agree or disagree with the statement in the box. Support your answer with a short explanation. So this is claim, evidence, reasoning, right? So your claim is agree or disagree. That would be the first words. Don't take the time to say, I would disagree or I would agree. Just say agree or disagree. And then you're trying to give a short explanation of what's going on, right? So if you want to take a stab at it, do you agree or disagree with what's in the box? And I've seen this more than once on the AP exam. So I've got 38. Let me just peek at a couple of the answers. So disagree. When water boils, its state changes. Disagree. Disagree. The water is not breaking apart. Disagree. Water vapor, which is H2O, this breaks intermolecular forces. Disagree. When you boil something, the intermolecular forces are broken. Okay, you guys got great answers. Great answers. Water boiling is a state change, and state changes break IMFs, not covalent bonds. Y'all are all over it. Great. Now, I know what y'all are thinking. Some of y'all are thinking, who misses this question? About 40% of the people that answer the question. That's who misses that question. In their head, they're thinking, oh, okay, yes, when water boils, it breaks into hydrogen and oxygen. They just get it wrong. But keep in mind, if you've ever made pasta or rice or just boiled water before, you know it doesn't turn into hydrogen and oxygen gas, because that would be flammable. So when you boiled water, it would turn into gases that could actually explode in your house, which would make Spaghetti, a very dangerous dish to make. All right, so here's another one. And again, this is based on data. So see if you can pick an answer that reaches out, says, yay, that's great. Choose an option of which one do you think is the best answer. The last one, sorry. Answer E is HF molecules tend to form hydrogen bonds. Answer choice E is HF molecules tend to form hydrogen bonds. And I will fix that next week. I will quit making things quite so big. So I got 34 answers so far. So what would give HF such a high boiling point out of all the other hydrogen halogen combos? All right, so let's see what y'all got so far. Lots of C's, lots of E's, a whole lot of E's. All right, and the correct answer is indeed E. So some of y'all said C. HF molecules have a smaller dipole moment. That's a fancy way of saying they're less polar, or they don't have as many, their dipole forces are not as strong. That's what C is saying. They have a smaller dipole moment, which means they're not as polar. Well, if that was true, you'd expect the boiling point to be lower than the other ones, not higher than the other ones. So HF, remember, to have a hydrogen bond, you have to have an H stuck to an F over N on one molecule, and then that's attracted to an F over N on another molecule. So that's why HF has such a high boiling point, because it forms those hydrogen bonds. All right, so this is another type question that they might have you look at, right? So the same molecule, 2 carbons, a bunch of hydrogens, turns out same number, and then 1 oxygen. But notice they're just arranged differently. And in chemistry, we call those isomers. So same basic empirical formula, or same molecular formula, but just arranged differently. So what would give ethanol, sometimes it's not a data table, sometimes it's in the text. So what would give ethanol a higher boiling point? Excuse me. What would give ethanol a higher boiling point? While y'all are answering, EP Oxford asked how ideal something to be a boiling point question. I don't think so. Ideal gases have more to do with does the pressure change? So things that are not ideal tend to deviate from the ideal gas law. So I think that's the only place you're going to see that. It used to be something, but it is no more. And then even then it was ideal solutions, not even ideal gases. So, all right, so let me see what some of the answers look like. Ethanol has hydrogen bonding. Dimethyl ether has a lower boiling point because it has weaker IMFs. Dimethyl only has LDFs, while ethanol has LDFs, dipole-dipole, and hydrogen bonding. Dimethyl ether would have dipole-dipole, that's true, and LDFs. Ethanol would have LDFs, dipole-dipole, and hydrogen bonds. This would happen because ethanol has hydrogen bonding, while dimethyl ether does not. Let's scroll down a little bit. Ethanol has strong, be very, very careful. Ethanol has stronger intramolecular forces. Whoever wrote that, that's inside the molecule. So make sure you get that it's stronger inter, T-E-R, molecular forces. So if you said that, I couldn't give you the point because it makes me think that you think LDFs happen inside the molecule. Right? So lots of great answers. Lots of great answers. So here's the basic point. Dimethyl ether is not just a hydrocarbon. Dimethyl ether actually will have a little bit of a polar quality because that molecule doesn't look like that. That molecule is actually bent. So that oxygen in the middle actually sits up top, and then the carbons come down at an angle. So that creates a little bit of a polarness to the dimethyl ether, whereas in the ethanol, the oxygen has is stuck to the hydrogen. So the ethanol can hydrogen bond. The dimethyl ether can't. And why can't it hydrogen bond? It has hydrogens because the dimethyl ether has hydrogen stuck to carbon, not to the oxygen. To have a hydrogen bond, you have to have a hydrogen stuck to F over N, and it has to be attracted to an F over N on another molecule. So dimethyl ether does not fit that, but ethanol does. So y'all did a great job of discussing both of them. Here's the dimethyl ether, here's the ethanol. Because the ethanol is higher, it has to have stronger intramolecular forces, and it has hydrogen bonding, whereas the dimethyl ether does not. Those are great answers. Great answers. All right, so don't answer this because you can't, right? So this is to show you how they build questions again. So we did this in Unit 1. Write the electron configuration. All right, I can do that. Roman numeral 2, A subpart 2. Explain why the radius is larger than the radius of the S atom. That's a periodic trends question. That's all about Coulomb's law. Which of the two species would be attracted into a magnetic field? Again, magnetic fields attract charged particles. The S2 minus ion is isoelectronic with the AR item. From which species is it easier to remove an electron? That's an ionization energy question. So we're still in Unit 1. In the H2S molecule, the HSH bond angle is close to 90. Which atomic orbitals are involved? That's a Unit 2 question. It's, can you draw a Lewis structure and come to some answer? And then part D, H2S has London dispersion forces and dipole-dipole forces. Compare the strength of the London dispersion forces to the strength of the London dispersion forces in water. So basically, remember what I said. When you have more electrons, you have greater London dispersion forces, and that's because of a fancy word called polarizability. So the more electrons you have, the greater the chance that they're going to become unevenly distributed, and that's called more polarizable. So the H2S has more electrons than the H2O, and thus it's more polarizable, and thus the H2S London dispersion forces are stronger than the London dispersion forces in water. And then the dipole-dipole forces in H2S compared to the dipole-dipole forces in H2O, that really comes down to who's more polar. And remember, polarity is a function of electronegativity. So who's more electronegative, the sulfur with the hydrogen or the oxygen with the hydrogen? And we know electric negativity goes up and to the right, and oxygen is above sulfur on the periodic table. And since it's above sulfur, then we would expect it to be more polar. All right, I'm going to skip this one real quick. We're going to skip this one real quick, so don't type in answer just because I feel like I'm running behind. See how SO2 melts at 200? Okay, that's just the thing. SiO2 melts at 1883. So here's the thing I want you to pay attention to. See how the melting point is not just higher, but it's ridiculously higher, Remember, I told you that some things are covalent network solids, and that silicon dioxide, this is one of those quartz, diamond, all those are going to have not just high melting points, but really high melting points. So the answer here gets into the SiO2, you're breaking those covalent bonds, which are everywhere. And the SO2, you're really just knocking out those intermolecular forces, all right? Okay, so this is kind of what I wanted to get to. You have covered at some point kinetic molecular theory. So kinetic molecular theory basically says that when you heat up a gas, those gas molecules get faster, right? If you've covered kinetics, you've probably also seen graphs like this. It's called a Morse distribution. And what you could tell is as the krypton gas got warmer and warmer, the range of speeds of the molecule got faster and faster and faster, right? So when something warms up, the curve kind of gets squished down and stretched out to the right. When things get colder, they kind of get smushed. The curve gets squished from the right and kind of rises up. So kind of get that in your head. Hotter means faster. What happens if all the things are at the same temperature? Well, the heavier a gas is, the greater its molar mass, the slower it's going to be moving. Because we say they have the same kinetic energy. Kinetic energy is a function of speed and mass. So if you have a greater mass, you can go a slower speed. So what I want you to notice is the heaviest gas there is radon. And radon has the peak, the middle of the peak is farthest over to the left, meaning it's the slowest gas. And which gas is the fastest? It's that very light blue one. And you notice that's helium. It's the fastest one. And they're all at the same temperature, so it's not about temperature. The fastest molecules are going to be the skinniest molecules. So the ones that don't weigh as much. So just keep those two things in your head. All right, so I want you to draw a box with particles, those same particles at 127 degrees. So using Pear Deck, go ahead and draw me a box just like that one, but show me 4 molecules just like that, but that are at a higher temperature. I can't wait to see your drawings. This is going to be great. One thing I want you to note about what they drew, see how not all the lines are the same length? That backs up to that graph that we were just looking at. Some of the molecules are going slow, some of the molecules are going fast, but we can calculate what we call an average speed or an average kinetic energy. So it's important that in the box, some are moving slow and some are moving fast. So it's showing that not all the molecules are going at the same speed. So let me look at y'all's answers. This is going to be great. All right. Some of y'all are neater drawers than others. That's fine. I can't draw for anything. Okay, so watch. Some of y'all drew more than 4 molecules. So keep in mind, the box on the left had 4 molecules. You can only have 4 molecules on the right-hand side. So whoever has 1, 2, 3, 4, 5, 6 molecules, you wouldn't get the point. So it has to be those same molecules. And in general, I think y'all are totally kicking butt because look, you've got the lines longer in the right-hand box, the one that you drew, they're longer than the one on the left, showing that you understand that when molecules get heated up, they get speeded up. All right? Great answers, great answers. So this is the ideal gas law. If you're a mathematical person, great for you. If you're not, just remember this equation is actually on the AP exam reference sheet. The volume always has to be in liters. The number of moles, of course, moles. There are 3 R constants on the AP exam reference sheet. You just need to pick the one that's the best for what you're doing. So if the pressure is given to you in atmospheres, then the R unit must be atmospheres. Just make sure you match it up. If the pressure is given to you in torr, you should use the R that goes with torr. And remember, the temperature always has to be in Kelvin. And if you forget that, look at the units of R, because the units of R have like Kelvin and moles and liters and everything you need to know. All right, so here is a graph with the hydrogen. On my same graph, if you will draw one for helium, they're both the same temperature. So if that's the line for hydrogen, what would the line for helium look like? And you don't have to make it dotted. You did on the AP exam, but here it can just be another color if you want to. I know drawing dotted lines is sometimes hard with a mouse. All right. Looks like I'm getting some good answers. Some of y'all have been doing kinetics recently because you're totally kicking butt on this graph thing. So keep in mind, you need to kind of go back and look at this as you get closer to the AP exam. Make sure you can do this because this is actually from an AP exam. So the important hallmark is it should start at the far left-hand side where the other graph starts. It has to, right? You can't make it start somewhere else. The peak you draw should go up higher than the existing curve. And then it should kind of swoop down and end before the end of the other curve. So the one I'm looking at right now on the shared screen is a good example of what it needed. It had to start at the same spot. It had to be higher than the initial curve. And it had to end before that initial curve. And the reason for that is helium's heavier. Helium has a molar mass of 4 and hydrogen has a molar mass of 2. So it should go slower because the bigger molecule goes slower, right? So if you aced that, then that was great. Y'all drew some great lines. All right, so gas is collected with a device. What volume would you record? So look at the thing and enter a number. You don't have to enter a unit, but what number would you enter for this particular device? This is called a gas collecting tube. And it also could be a burette. They're both kind of read the same way. Okay, so let's see what y'all got. It's kind of hard to see exactly what it is. All right. All right, so the correct answer there would have to be in between 42 and 43. So the correct answer could not be 43.5, right? Because it's between the 42 and 43. So the correct answer here would be 42.4. And then since the lines are reading to the tenths place, so it's reading to 1 decimal place, whenever we read a device, we go 1 more decimal place than what the line suggests. So the lines read to the 1st decimal place on the device. So we would want to go ahead and guesstimate that 2nd one. So the correct answer here would be something like 42.48, 42.47, 42.45, anything like that would be fine, as long as it had 42.4 something. And to me, it's farther close, it's pretty darn close to 42.5. All right, so what are you supposed to do with this number? So in this particular gas law problem, they want you to find the pressure of the hydrogen in the tube. Now, the chemical reaction produced hydrogen and it bubbled up through the water into the tube. But you have to remember that when you bubble water through a tube, there's not only just that gas in there, or sorry, when you bubble gas through water, there's not only that gas in the tube, there's also water vapor. So for part A, go ahead and find the pressure of just the dry hydrogen in the tube. And then with the information given, see if you can calculate the moles of hydrogen in the tube. And you would have to use a calculator for this one. I know it's 8 o'clock, and if you guys have to go, I understand. I'm going to keep going because I want to cover a couple more things. All right, y'all are doing great on the first part. So the first part, basically what it's saying is the total pressure is 757. The pressure, the water vapor pressure is 19 of that. So to find the pressure of the hydrogen, you're just really taking the 757 minus the 19. That's how you find the pressure of the hydrogen in the tube. All right, so let's see what y'all are getting. Looks like a lot of y'all are stuck on part B. Some of y'all are getting the right answer, and some of y'all are getting very close to the right answer. So let's go over how to do this. So to calculate the moles, remember in PV equals nRT, N is the number of moles. So that's what we're looking for. So that means N is going to be equal to P times V divided by R times T, right? So just move it around until you get N all by itself. Now, what is the P? Well, the P is the pressure of the hydrogen. So you have to take your answer from part A, 738 millimeters of mercury. And then what is the V? The volume is the volume of the hydrogen in the tube. So it wouldn't be 42.48 milliliters. Remember, you have to put it in as liters. So it'd be 0.04248 liters. So some of y'all were off by 1,000, and I think that's why you were off by 1,000. And then R, if you have the reference sheet, is 62.4. That's the value. And then the temperature here is got to be in Kelvin. So 21 Celsius, you can't plug in 21. You'd have to add 273. And so the temperature here would be 294. And I got an answer of 0.00171 moles. 0.00171 moles. Right. So that's the kind of PV equals nRT question they might ask you on the AP exam. Oops. All right. right? Just to show you, in a multiple choice format where you don't get a calculator, sometimes they'll ask you to solve a pertinent problem, but instead of, oh, give me an answer, they'll say, which one is the best setup? So you would have to be able to plug into PV equals nRT, solve for P, and make sure you're plugging the right numbers in here. So the moles would be 1.85. The R, because it's in atmospheres, would be 0.0821 or 0.08206 now. This is an older question. And the temperature couldn't be 35. The temperature would have to be in Kelvin, so you'd have to add 35. And that's where they're getting that 308. So you just want to pick the one that gives you the best setup. And y'all can just drag the icon wherever you think it should go. So you've got a icon, which one do you think is the right answer to find PV equals nRT when you solve for P, the pressure? All right, so a lot of y'all are picking A. A couple of y'all are picking D, and D is not a horrible answer. The problem with D is it's the wrong R value. So when you're looking for atmospheres, you're using 8.314s, which doesn't have atmospheres in it. So you'd want the R unit that goes off the reference sheet that goes with atmosphere. So the correct answer there would be A. All right, so I wanted to make sure I get to this one, and we'll probably end pretty close to this one. I'll see if I can find one more that we need to do. But students oftentimes struggle with this kind of question. A sealed vessel contains this gas, this gas, and this gas. The total pressure is 5 atmospheres. What is the partial pressure of the argon? Okay, so if you want to take a stab at it, go ahead and enter a number. So if the total pressure is 5 atmospheres, how much of it is the argon gas? All right, so let's see. Getting numbers a little bit all over the place, but a lot of y'all are picking 2. All right, so this is how the setup of this goes. Here's how the math works. Argon is 0.2 moles out of a total of 0.5 moles. Add all the number of moles together. So if it's 0.2 out of 0.5, that means it's 2/5 of all the moles. And if it's 2/5 of all the moles, then it has to be 2/5 of the total pressure. So 2/5 of 5 atmospheres ends up being 2 atmospheres. So if you got that one right, great job. All right, so we'll end on this one. I'm going to get y'all to basically pick the one, draw anywhere on the slide. I want you to circle the one that looks like it's the right drawing that goes together with that equation. Part of this is solutions, and I know I didn't spend a lot of time on solutions, but trust me, you're going to be doing so many labs and you're doing acid-base, equilibrium and stuff. Trust me, you're going to be doing enough solution stuff that I think you'll be good to go. Molarity should not be a big thing for you. But which one of those particulate level drawings, sometimes they'll give you them, sometimes they'll ask you to draw them. Which one of them is the best depiction of what's going on? Just draw, circle the one on the slide that you think is the right one. Excuse me. The question doesn't really say which one was in excess or anything like that. So let me peek at some of your answers and then we're going to wrap it up. All right. So that one in the middle, some smiley faces, crossed out stuff, always good. I think your teachers have been doing an awesome job if y'all are getting the right answers. So I love it, love it, love it. Oh, and Earth, very nice. Great job. Okay. Oh, there's a sad face. I'm so sorry you have a sad face. All right. So this is a good way to figure out what ain't the answer, right? Well, it says you should have a precipitate. So the first one is out because it doesn't have a precipitate. This one on the far right, upper right-hand corner, it's wrong because you shouldn't have any I minus left over, right? And if you look at the balanced equation, notice that for every 2 NAs, there's also 2 NO3s. So if the Na and the NO3 are spectator ions, then we would expect them to be in the beaker in the same ratio. So if you're going to have 1, 2, 3, 4, 5 sodiums, then you should also have 5 nitrates. If you have 4 sodiums, you should have 4 nitrates. So it's not just about the precipitate. It should also be about, are they in the right proportion? That's also what the problem with the bottom left one is. You shouldn't have any lead left over, and the sodium and nitrate should be in the same proportion, 1 sodium for every 1 nitrate. And the bottom right one is wrong because nitrate should not, nitrate should be a spectator ion, and it's not there. So ASFA Susan, this particular question did not get into amounts and how do you know, but the ones that are wrong that you might go, oh, well, this could be an excess. If it was an excess, then we would expect different drawings. So these drawings are very much in line with like there's only one right answer. The years where they do that, they go to great lengths to say things like, the sodium iodide is in excess. So you should have excess of those things and that kind of thing. This was just 7 back in the day where it basically just said, hey, can you pick out the right picture? The ones now are actually a little bit harder. So. All right, so I'm going to go ahead and close it there. If you guys have any more questions, feel free to ask. Thank you for coming tonight and sticking with me. This was a long one. The next one will be Unit 4. It's shorter, so I promise not to go super long. This is the longest unit of the entire thing. So if you guys could go ahead and log off. Thank you for coming. And if you have any, I'll be happy to stick on for another minute and answer any questions you have.